An Introduction to Set Theory and to Philosophy and Methodology of Mathematics and Computer Programming by Jan Plaza.
The sets of numbers, an overview. Let us introduce some notation for various familiar sets of numbers. Z stands for the set of all integers. Z plus positive integers. N natural numbers, which means non-negative integers. The difference between positive and non-negative is that 0 is included among non-negative integers. 0 is not negative, but 0 is not a positive integer. Q, the set of rational numbers. R, the set of reals or real numbers. R, with the subscript greater than or equal to 0, non-negative reals. And C, complex numbers. To remember this notation, I can add that the letter Z used for the set of integers comes from the word Zahl, which in German means number. Q could be thought as coming from quotients, because rational numbers are quotients of integers. So what relation do we have between these sets? Z plus is the smallest of them. It involves 1, 2, 3, and so on. The set of natural numbers additionally involves the 0. Then we have the full set of integers, which contains all the previous ones, but also negative integers. The next is the set of rational numbers, which involves numbers such as 1, 2, 2/3, and so on. Then we have the set of real numbers, and beyond that, the set of complex numbers. In real numbers, there are numbers such as pi, square root of 2, e, the base of natural logarithms, and so on. These numbers are known not to be rational. However, they are real numbers. And you might have studied before complex numbers, The square root of -1 is denoted by I. This is one of the complex numbers. If we were to write this relationship using symbols, we would say that Z plus is a proper subset of natural numbers, which is a proper subset of integers, which is a proper subset of rational numbers, and then real numbers and complex numbers. When we consider numbers in set theory, we assume that they are represented as sets. On some earlier occasion, I mentioned that we'll use the empty set as a representation for the number 0. Similarly, there is a specific set representing the number 1, another set representing number 2, and so on. Zermelo-Fraenkel set theory, ZFC, if we add the axiom of choice, can be considered a foundation of mathematics because not only numbers, but almost all mathematical objects can be represented as sets. As numbers are represented as sets, we should expect that arithmetic can be formulated not as a separate theory, but as a fragment of the set theory. We'll see a little bit of that more, a little more of that later. And in the context to computers and programming, let me mention that representing some objects by means of more basic ones is a useful trick. So not only numbers are represented as sets in our set theory, but also in programming, actually everything is represented as sequences of bits. At a higher level of abstraction, programmers use the same trick to define new objects in terms of objects built into the language. And one more remark. Sometimes we hear a phrase, a binary number. Strictly speaking, however, strictly speaking, there is no such a thing as a binary number. A more precise phrase would be the binary representation of a number. And the presentation being an expression. Every number can be represented in the binary system, base 2, and alternatively can be represented in the decimal system. For instance, the number 2 is written as 1, 0 in binary. The same number is written as 2 in decimal. They do not represent. Let me write the base as a subscript. So 1, 0 in binary and 2 in decimal. These do not represent different numbers. It's just one and the same number written using two different expressions. And here is a comment a student emailed me once. The email said, there are that many kinds of people. Those who understand binary and those who don't.